Hi guys, surprise, it's me. I'm sure you're surprised to not see Dooley, but we're going to accelerate things by forcing you to watch two videos and learn about two different things today. So today I'm talking about Newton's third law, and Mr. Dooley is going to talk about friction. We've talked about Newton's first law, which equates mass to the difficulty to move something or to change its motion, I should say, and Newton's second law, which looks at the mathematical relationship between force, mass, and acceleration. Today, I want to look at Newton's third law. So if we look at this, whoa, this ghost on a skateboard is demonstrating Newton's third law. And Newton's third law tells us for every action, there's an equal and opposite reaction. What that really means in terms of physics is that for every force, there's an equal and opposite force. All forces have to come in pairs, and we call them action-reaction pairs. So if we look at this ghost pushing against the wall, the force that the ghost is putting on the wall is to the left, but they're going to move to the right because the wall is putting just as much force on that person. So the person's force is the action force. The force from the wall is the reaction force. So the wall is putting just as much force on the person. Now, the free body diagram would not use the person's force on the wall. If we're looking at the free body diagram based on the person, we would look at the force on the person from the wall. So we don't always do the action-reaction pairs of forces in a free body diagram. In fact, we're looking only at the forces acting on something, not what the forces that thing is doing to other stuff. So we're not looking at, if we're analyzing the motion of the ghost, we're not looking at the force the ghost is putting on things, we're looking at the forces acting on the ghost. So we would typically have a free body diagram that has the wall's force on the person, and friction acting against that person. So that would be going to the left. That would be less than the wall's force on the person because that would cause a net force to be in the right direction to cause the person to accelerate to the right while they're pushing. And then we'd have gravity pulling down and the force of the floor pushing up. So we have all kinds of different action-reaction type of pairs. But the thing is, no force can exist without an equal but opposite force. It just can't happen. So I've got here two force detectors that tell me forces. So if we look at this and I hit collect on here, this one, if I pull it, will give us that, and this one will give us that. If we connect them together and pull, we can see that they are exactly opposite each other when we see the forces. I can't pull on one without pulling on the other. I can't push on one without pushing on the other. It's exactly opposite. So when we have situations where there is a force on something, that means the exact opposite force is being done by that thing. So this is how we figure out how to move in a lot of different ways. If you're swimming, you put force on the water. The water then puts force on you and causes you to move. Technically speaking, a car is not being propelled by the wheels, it's being propelled by the ground because the wheels are pushing backward on the car and the ground is pushing forward back on the wheels and causing the car to go forward. The fact that the air does not have enough resistance to keep the car from accelerating is where we look at free body diagrams and predict the acceleration, all right? When a bird flaps its wings, it's flapping the wings and it is pushing down on the air is pushing it up, it allows it to fly. So when we talk about Newton's third law, we always have to account for the exact opposite force in the opposite direction from what's happening. The net force on an object will cause the object to move, but the object is putting force on the things around it. So when the imbalance of forces on the object occur, that's what causes it to move. So if you think about like a tug of war, the two teams cannot pull any more than each other on the rope. The force on the rope is the same in either direction. The team that wins is a team that puts more force on the ground. So we have an imbalance of forces on the ground, not an imbalance of forces on the rope. The rope can't have a different amount of force on it from one team than the other. Okay. One of the big confusing things can be if I drop a ball, we know that ball accelerates. So what is the equal and opposite reaction force when I drop a ball? All right. Well, here's the thing. That question, the way I ask it, is difficult to answer because obviously there's a force on the ball, the force of gravity on the ball, and there's a force of air resistance, but those are not equal and opposite because the ball is accelerating downward. But if I ask it this way, the earth is pulling down on the ball, what is the equal and opposite force? The ball is pulling up on the earth. Now, the reason we don't think of it that way is because there's such a massive difference in the ball and the earth that we don't know, we can't comprehend that the earth is moving up to the ball. But if I actually drop a ball like this, did you feel the earth move? Exactly. We didn't feel the earth move because it's so massive, it has so much inertia that it's difficult to comprehend that it's being pulled up. But technically speaking, it is being pulled up. So if we look at this, how much would a ping pong ball cause the earth to accelerate? All right, if you drop a ping pong ball, the ball accelerates towards the earth, and we know that it accelerates at 9.81 meters per second per second. The earth happens to accelerate upward towards the ping pong ball as well. All right, here's how we solve that. We take the force of the ping pong ball is equal and opposite the force of earth. The mass of the ping pong ball times its acceleration, because F equals ma, is equal to the mass of the earth times its acceleration. So we can find the acceleration of the earth by taking the mass and acceleration of the ping pong ball. In other words, the weight of the ping pong ball, 0.0027 kilograms, is the mass of a ping pong ball times 9.81. And divide that by the mass of the earth. Now, the mass of the earth is known. And so we have to look that up, 5.97 times 10 to the 24 kilograms. If we find that, then we'll see that the earth actually accelerates up at 4.4 times 10 to the negative 27 meters per second per second. That's not much. In fact, it's imperceptible to us. But it is a valid calculatable number. All right. So the big thing to take away from this is when we have a force, there is always an equal and opposite force that's acting on the object that is the forces are participating with. So we call those action-reaction pairs, and we use one of those of each pair when we're doing a free body diagram. We're not worried about what the object moving is doing to its surroundings. We're worried about what the surroundings are doing to the object. So we're going to talk about this in terms of friction with Mr. Dooley in the next video lesson. All right. Thanks a lot. Have a great day.